Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Matteo. Welcome to our show. Let's talk about physics.
In the 10th episode of this series, let's talk about combining quantum mechanics with Einstein's special theory of relativity.
Einstein's 1905 breakthrough, the special theory of relativity. Fast forward 20 years, Schrödinger knew of Einstein's work. He discovered the Klein-Gordon wave equation, a relativistic wave equation. But those strange solutions, negative kinetic energy, too exotic. So Schrödinger published his non-relativistic wave equation instead. And that's how the Schrödinger equation became legendary.
Anya, I agree with you.
Schrödinger's decision was spot on, earning him the Nobel Prize in Physics in 1933. Like in classical mechanics, in non-relativistic quantum mechanics, particles always have positive kinetic energy. Schrödinger's wave equation is the first students learn in quantum mechanics. Meanwhile, Klein and Gordon independently published their own wave equation. Their equation is the first relativistic wave equation students encounter. Today, we know relativistic equations can have exotic solutions. These solutions show particles with negative kinetic energy. Quantum mechanics continues to intrigue and challenge our understanding. The legacy of Schrödinger, Klein, and Gordon lives on in physics. Their discoveries paved the way for modern quantum theories.
Dear Matteo, you are well informed.
In 1928, Dirac discovered a new wave equation. He was able to make sense of the existence of exotic solutions with negative kinetic energy. In 1933, Dirac and Schrödinger shared the Nobel Prize. In 1936, Anderson discovered the positron, the antiparticle of the electron. He received the Nobel Prize for this in 1936. These discoveries proved antimatter's existence. Antimatter existence supports Einstein's special theory of relativity.
Anya, you know a lot. Let's summarize our discussion today.
Non-relativistic quantum mechanics is like the classical world, but with a twist. The Schrödinger wave equation is our guiding star, with solutions that feel familiar. Just like in classical mechanics, particles here always have positive kinetic energy. But when we dive into relativistic quantum mechanics, things get wild. The Klein-Gordon equation is simple, but Dirac's equation steals the show. Here, exotic solutions emerge, where particles have negative kinetic energy. These are linked to antimatter, a whole new frontier.
Matteo, we should add a comment about the Grave de Peralta's equations.
A century after Schrödinger's equation, Professor Grave de Peralta made a groundbreaking discovery. He found a pair of equations that unlock both common and exotic solutions to the Klein-Gordon equation. These equations resemble Schrödinger's, unifying relativistic and non-relativistic quantum mechanics.
Yes, Anya. We will talk about this in the next episode. Ciao, Anya. I love you, and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 11th episode of this series, let's talk about combining quantum mechanics with Einstein's special theory of relativity by using the Grave de Peralta's equations.
Like classical particles and non-relativistic quantum particles, relativistic quantum particles can be in common states with positive kinetic energy. In addition, relativistic quantum particles could be in exotic states with negative kinetic energy. Relativistic wave equations must have common and exotic solutions. For free quantum particles, there is a pair of Schrödinger-like but relativistic Grave de Peralta equations. One only has common solutions and coincides with the Schrödinger equation in the non-relativistic limit. The other Grave de Peralta equation only has exotic solutions with negative kinetic energy.
Anya, I agree with you.
In the realm of quantum physics, non-relativistic particles have a common wave. This wave emerges from solving the Schrödinger equation. Classical particles, however, don't have any associated wave. But when it comes to relativistic quantum particles, things get interesting. They have two waves, one common and one exotic. These waves are derived from Grave de Peralta's equations. Yet, the nature of these quantum waves remains a mystery.
Dear Matteo, you are well informed.
Most of the fascinating properties of quantum particles are related to the quantum wave associated with them. This is why classical particles do not have these properties. Quantum particles can be simultaneously in several states, can be entangled, and teleported. Imagine a world where particles exist in multiple places at once. Entanglement means particles are connected no matter the distance. Teleportation isn't just sci-fi, it's a quantum reality.
Anya, I agree with you.
Classical particles don't have waves, but quantum particles do. There are two types of waves, common and exotic, in quantum particles. The fascinating properties of quantum particles come from common waves. Quantum antiparticles' properties are linked to exotic waves. Exotic solutions in wave equations hint at antimatter. Antimatter's existence supports Einstein's special relativity.
You are correct, Matteo. Antimatter exists.
Every day, antimatter particles are detected in particle accelerators. Yet, matter is far more abundant in nature than antimatter. The reason for this imbalance remains a mystery. Nevertheless, Professor Grave de Peralta has an intriguing hypothesis.
Anya, you know a lot. Let's summarize our discussion today.
In classical physics, particles don't have waves. But in quantum physics, non-relativistic particles share a common wave. This wave gives quantum particles their unique properties. That's why classical particles lack these fascinating traits. For relativistic quantum particles, there are two waves. One is common, the other exotic, linked to antimatter. These waves are solutions to Grave de Peralta's equations. They extend the Schrödinger equation to the relativistic realm. Understanding these waves unlocks the mysteries of quantum mechanics.
Matteo, we should add a comment about vacuums.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe, to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 12th episode of this series, let's talk about vacuums.
The original vacuum concept was just an empty place. Physicists thought waves needed a medium for propagation, so they invented the ether. Then Maxwell's equations showed light can travel through vacuum. Einstein's relativity kicked the ether out of the vacuum. This is the classical cosmological vacuum. But Dirac introduced the Dirac sea for quantum states. Now, the quantum vacuum is like boiling water. Particle-antiparticle pairs pop in and out of existence.
Anya, I agree with you.
The cosmological vacuum was once thought to be empty, until the universe's expansion was discovered. Physicists then imagined it filled with dark energy, a mysterious entity driving the cosmos. Quantum physicists soon proposed that cosmological and quantum vacuums were the same. Yet, there's far less dark energy in the cosmological vacuum than zero-point energy in the quantum one. Recently, Professor Grave de Peralta suggested the cosmological vacuum is classical, due to its massive associated mass. This mass is much larger than the Planck mass, confirming our understanding of a classical universe.
Dear Matteo, you are well informed.
Imagine a boundary where classical and quantum worlds meet, the Planck mass. This frontier suggests that large objects, like galaxies, must be classical. So, the vast cosmic vacuum is classical, almost empty, and governed by relativity. This implies quantum vacuums have limited energy, tied to Planck mass particles, a universe where the smallest scales define the largest realms, the cosmic dance of relativity and quantum mechanics in perfect harmony, a frontier that confirms our intuition about the universe, where classical rules reign over the vastness of space, and quantum limits shape the energy of the void.
Anya, I agree with you.
Dirac created the Dirac's sea to make sense of exotic quantum states. The Dirac's sea is the set of all the energy states obtained from a relativistic wave equation. All the exotic states were supposed to be occupied by unobservable quantum particles, and all common states were empty. An observable particle appears when a particle jumps from an exotic to a common state. This creates a bubble in the Dirac sea. The bubble is associated with the creation of an antiparticle.
You are correct, Matteo. The Dirac sea concept conducted to modern field theories.
The Dirac sea concept has a problem. How come there are an infinitude of unobservable quantum particles in the quantum vacuum? Theoretical physicists used a mathematical trick called second quantization for transforming quantum waves into quantum fields filling the vacuum. Particle-antiparticle pairs come to ephemeral existence from these fields. But there is a problem. In contrast with reality, field theories predict a universe with equal number of particles and antiparticles.
Anya, you know a lot. Let's summarize our discussion today.
Imagine the modern quantum vacuum, like boiling water, where particle-antiparticle pairs continuously pop in and out of existence. These pairs emerge from quantum fields, only to vanish moments later. But here's the catch. Field theories predict a universe with equal number of particles and antiparticles. Yet, in reality, our universe is dominated by particles. This imbalance is one of the great mysteries of physics. It's like expecting a balanced recipe, but ending up with too much of one ingredient. The quest to understand this cosmic puzzle continues.
Matteo, now we should talk a little bit more about antimatter.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 13th episode of this series, let's talk about antimatter.
In the quantum world, every particle has a twin, its antiparticle. These pairs emerge from the quantum vacuum, a mysterious realm of potential. When they meet, they annihilate, vanishing back into the void. This dance of creation and destruction is a daily spectacle in particle accelerators. Even the elusive antiatom of hydrogen has been captured in experiments. Yet, antimatter remains a ghost in our everyday world, its absence a cosmic mystery.
Anya, I agree with you.
Ever wondered about the universe's hidden twins? Meet the positron and electron. Identical, yet opposites in charge. Then there's the proton and its shadow, the antiproton. Hydrogen, the building block of life, has an antimatter twin, but anti-uranium? That's still a mystery to us. While students memorize the periodic table, only light antimatter atoms are real, and that's why most folks don't lose sleep over antimatter.
Dear Matteo, you are correct, but antimatter is very important in physics.
Modern field theories are matter-antimatter symmetric. They predict as much antimatter as matter, yet it's missing in our daily lives. Physicists use a scapegoat to explain this discrepancy. Something happened 13 billion years ago at the universe's start. This event produced an excess of matter over antimatter. The mystery of missing antimatter remains unsolved.
Anya, I agree with you. This explanation is a scapegoat because it will be extremely difficult or impossible to prove or disprove such an explanation.
Ever wondered why there's no life made of antimatter? Life as we know it is made of atomic matter. We humans are made of matter, and if aliens exist, they'll be made of matter too. Why doesn't biological antimatter exist? It's a fascinating question. The scapegoat answer is that biological antimatter can't exist without antimatter. But recently, Professor Grave de Peralta offered an intriguing alternative.
You are correct, Matteo. Grave de Peralta's answer to the question, why does biological antimatter not exist, is very interesting.
Anya, you know a lot. Let's summarize our discussion today.
Antimatter is made of antiparticles, a mirror to the particles we know. In the quantum vacuum, particles and antiparticles dance in equal numbers. Modern theories predict as much antimatter as matter, yet it's missing in our daily lives. Why is antimatter absent? It's a mystery that baffles scientists. Chemistry students study the periodic table, but only the lightest antimatter atoms exist. The universe holds secrets, and antimatter is one of its greatest. Antimatter, the universe's hidden puzzle waiting to be solved.
Matteo, we should discuss about biological antimatter.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 14th episode of this series, let's talk about Professor Grave de Peralta's answer to the question, why does biological antimatter not exist? In previous episodes, we discussed that classical attractive fields could produce quantum waves collapses.
In the quantum realm, particles dance to a different tune. Non-relativistic particles have common quantum waves, unlike classical ones. This absence of quantum waves is why classical particles lack quantum traits. Relativistic particles, however, boast both common and exotic quantum waves. In atoms with atomic numbers over 137, strong electric fields collapse common waves. This collapse limits the periodic table to around 100 elements. Gravity fields collapse common waves in particles over the Planck mass. Thus, macroscopic objects are classical, while atoms remain quantum. Professor Grave de Peralta suggests strong repulsive fields could collapse exotic waves. This could redefine our understanding of quantum antiparticles.
Anya, I agree with you.
Professor Grave de Peralta's hypothesis sheds light on why only light antimatter atoms exist. If the antiparticle's charge exceeds Planck's charge, its exotic wave collapses. This means positronic clouds with over 11 positrons become classical objects. Quantum mechanics explains atomic stability for atoms with atomic numbers under 137. Here, electronic clouds remain quantum objects, forming stable atoms. However, positronic clouds with more than 11 positrons are classical. Thus, antimatter atoms with over 11 positrons can't maintain stability.
Dear Matteo, you are well informed.
Notably, exotic waves associated with electronic clouds with more than 11 electrons exist. This is why atoms with atomic numbers larger than 11 exist. Professor Grave de Peralta's hypothesis breaks the wrong matter-antimatter symmetry of current fields theories. Antiparticles differ from particles in how their exotic waves react to strong repulsive electrical fields. Exotic waves of positronic clouds with more than 11 positrons collapse. but exotic waves of electronic clouds with more than 11 electrons do not.
Anya, I agree with you.
Ever wondered why there's no life made of antimatter? Life as we know it is made of atomic matter, and so are we humans. If aliens exist, they'd be made of matter too. Why doesn't biological antimatter exist? It's a great question. The easy answer? Biological antimatter can't exist without antimatter. And there's no antimatter because, well, the scapegoat. But Professor Grave de Peralta has a different take. He says life made of antimatter is impossible without antimatter chemistry. So, no antimatter chemistry, no biological antimatter. Fascinating, right? Stay curious.
Matteo, this is a sensational result and interpretation. This makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
Anya, you know a lot. Let's summarize our discussion today.
Strong, repulsive electric fields can collapse the exotic wave of electrically charged quantum antiparticles. If the absolute value of the antiparticle's charge is larger than Planck's charge, the exotic wave collapses. The Planck's charge is approximately equal to 11 times the positron's charge. Antiparticles differ from particles in how their exotic waves react to strong repulsive electrical fields. I emphasize repulsion, the opposite of attraction. Positronic clouds with more than 11 positrons collapse, unlike electronic clouds with more than 11 electrons. This is how Professor Grave de Peralta's hypothesis breaks the wrong matter-antimatter symmetry in current fields theories. Biological antimatter does not exist because life made of antimatter is impossible without antimatter chemistry.
Matteo, we should add that current field theories have been extremely successful describing matter. Unfortunately, they predict an inexistent antimatter world. I think that we should review the details of Professor Grave de Peralta's hypothesis.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 15th episode of this series, let's talk about the details about collapse of exotic waves due to strong repulsive electrical fields. In previous episodes, we discussed how strong attractive electric fields could produce common quantum waves collapses. We also covered the gravitational atom model.
Imagine a quantum particle trapped in a box, the simplest model for spatial localization. Using a Grave de Peralta's equation, we find the positive relativistic kinetic energy. This energy is a rough estimate of the internal kinetic energy in gravitational atoms. For potential energy, we consider the negative gravitational potential. The total energy of the quantum particle with mass is the sum of kinetic and potential energies. The quantum wave size is estimated at the minimum energy level. This model offers a glimpse into the complex world of quantum mechanics.
Anya, I agree with you.
Imagine repeating calculations, but first, swap positive kinetic energy with negative energies of exotic solutions. Next, replace negative gravity potential with a positive repulsive Coulomb potential. Then find a local maximum of total exotic energy. The result? Mind-blowing. The exotic wave of a charged quantum antiparticle collapses if its charge exceeds Planck's charge. That's about 11 times the charge of a positron. Physics just got a whole lot more interesting.
Dear Matteo, you are well informed.
In this way, it was determined that the exotic waves of cloud of charged antiparticles, like positrons, can't exist if its total charge exceeds the Planck charge. This is because the exotic quantum wave of the cloud collapses. A cloud of more than 11 positrons becomes a classical antimatter object. This explains why only a few lithe antimatter atoms exist. Notably, this wouldn't happen if the non-relativistic Schrödinger equation was used. The absolute value of the relativistic kinetic energy is smaller than the non-relativistic one. Therefore, large positronic clouds lack enough kinetic energy to compensate for potential energy. The paper Classical Fields and the Existence of Classical Quantum Frontiers, published in 2025 on social media X, confirms this result. Moreover, Grok, the AI of X, confirmed its validity. This result was interpreted as the existence of a quantum classical frontier at the Planck charge for antimatter. This is because the quantum antiparticle gets nude after the collapse of the exotic quantum wave. An antiparticle without waves is a classical antiparticle.
Anya, I agree with you.
Imagine a cloud of electrons, more than 11, swirling in quantum harmony. This means a cloud of electrons with more than 11 electrons continue being quantum. Therefore, there are stable atoms with more than 11 electrons. Thanks to Professor Grave de Peralta, we know why. He proposed that their repulsive potential energy in exotic states isn't positive, but negative. This keeps atoms with more than 11 electrons stable. Antiparticles and particles differ in their exotic wave reactions. Strong repulsive fields influence them uniquely. So, stable atoms thrive, defying collapse. Quantum magic, right?
Matteo, this is a sensational result and interpretation. This makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
Ever wondered why there's no life made of antimatter? Life as we know it is made of atomic matter, and so are we humans. If aliens exist, they'd be made of matter too. Why doesn't biological antimatter exist? It's a great question. The easy answer? Biological antimatter can't exist without antimatter. And there's no antimatter because, well, the scapegoat. But Professor Grave de Peralta has a different take. He says life made of antimatter is impossible without antimatter chemistry. So, no antimatter chemistry, no biological antimatter. Fascinating, right? Stay curious.
Matteo, this is a sensational result and interpretation. This makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
Anya, you know a lot. Let's summarize our discussion today.
Imagine a world where strong repulsive electrical fields can collapse antiparticle exotic waves. Yet, these same fields extend particle exotic waves. This is the essence of Professor Grave de Peralta's groundbreaking hypothesis. Current field theories excel at describing matter, but they predict a non-existent antimatter world. Could Grave de Peralta's hypothesis introduce matter-antimatter asymmetry into these theories? It's a revolutionary idea that challenges the very foundation of our understanding.
Matteo, we should now summarize the complete series.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 16th episode of this series, let's talk about quantum electrodynamics.
Quantum electrodynamics was the first modern field theory, a new version of relativistic quantum mechanics. It became the template for all current field theories. In Dirac's original model, particles and antiparticles shared states with both positive and negative kinetic energy. Particle-antiparticle pairs constantly emerge from and return to the quantum vacuum. Dirac's C model had an issue. An infinite number of unobservable particles filled the vacuum. A mathematical trick called second quantization transformed quantum waves into quantum fields. Now, particle-antiparticle pairs emerge from and return to quantum fields, resolving the issue. The infinite sea of unobservable particles disappears in quantum electrodynamics.
Anya, I agree with you.
Quantum electrodynamics is the first modern field theory, born from the genius of Dirac. Dirac previously pioneered the use of the Klein-Gordon and Dirac equations for relativistic quantum mechanics. Quantum electrodynamics precisely describes how electrons and positrons interact with photons. It is an extremely successful theory. Tominaga, Schwinger, and Feynman were awarded the Nobel Prize for their contributions. Quantum electrodynamics is inherently quantum, matter-antimatter symmetric with no quantum classical frontiers. Therefore, quantum electrodynamics predicts the existence of an inexistent antimatter world and does not predict the classical nature of macroscopic and cosmological objects.
Dear Matteo, you are well informed.
In experiments, particles and antiparticles always have positive kinetic energy. In Dirac's original theory, antiparticles as common states linked to particles' exotic states. By flipping the kinetic energy sign of an exotic electron-free state, we get a positron's positive kinetic energy. In quantum electrodynamics, particle-antiparticle pairs always emerge with positive kinetic energies. Yet, Feynman diagrams show positrons moving backward in time, a curious mathematical trick. Grave de Peralta's theory aligns more with Dirac than with quantum electrodynamics.
Anya, I agree with you.
In Grave de Peralta's relativistic quantum mechanics, a pair of equations with both common and exotic solutions are used. Imagine transforming these waves into fields through second quantization. It's speculative but promising. We could see a new era of quantum electrodynamics that handles particles and antiparticles with ease, and also might finally address matter-antimatter asymmetry and quantum classical frontiers. It's an exciting topic of research, waiting to be explored and understood.
Matteo, this is an excellent topic of investigation for young theoretical physicists.
Anya, you know a lot. Let's summarize our discussion today.
In the world of physics, there are several takes on relativistic quantum mechanics. The most accepted? Quantum electrodynamics. It transforms quantum waves into fields using a second quantization procedure. Quantum electrodynamics was the first modern field theory. It's the blueprint for all current field theories. These theories excel at describing quantum particles and antiparticles interacting with photons. But they fall short in predicting quantum classical frontiers and observed matter-antimatter asymmetry. Could Grave de Peralta's hypothesis bridge these gaps? Could it introduce quantum classical frontiers and matter-antimatter asymmetry?
Matteo, I think that many young theoretical physics will be tempted to answer this question.
Anya, I hope we will know the answer very soon. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe, to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 17th episode of this series, let's talk about primordial black holes, antimatter sinks, and the absence of antimatter in our everyday lives.
Primordial black holes, hypothetically born at the dawn of the universe, are more massive than the Planck mass. Their existence hints at the mysterious quantum classical frontier. Quantum particles and atoms are the unsung heroes of stability in our world. They ensure electrons don't collapse into the nucleus, keeping atoms intact. From particles to atoms, atoms to molecules, and molecules to cells. This is the story of creation. Cells endure, forming the complex tapestry of life, including us.
Anya, I agree with you.
Imagine the universe's first second, a cosmic dance of creation. Tiny mass fluctuations, smaller than the Planck mass, spark into existence. These fluctuations birth the elemental quantum particles and antiparticles we know today. No elemental quantum particle exceeds the Planck mass, a cosmic rule of balance. But when mass fluctuations surpass the Planck mass, something extraordinary happens. Classical primordial black holes form, potential keys to the universe's dark matter mystery. These ancient relics might just be the missing pieces of a cosmic puzzle.
Dear Matteo, you are well informed.
Imagine a universe where antimatter sinks exist, just like primordial black holes. These antimatter sinks might have formed in the first second of the Big Bang. They could explain why there's more matter than antimatter in the universe. Tiny pairs of charged matter and antimatter fluctuations could create known elemental particles and antiparticles. This aligns with the fact that no elemental particle has a charge larger than the Planck charge, but larger antimatter fluctuations might form classical primordial antimatter sinks. These sinks could be the missing antimatter we've been searching for.
Anya, I agree with you.
There's a quantum classical frontier at the Planck charge, but only for charged antimatter. This means there are no charged matter sinks. And where is the missing antimatter in the universe? It could be hidden in primordial antimatter sinks. These ideas were discussed in the paper Classical Fields and the Existence of Classical Quantum Frontiers, published in 2025 on social media X, formerly Twitter. Moreover, Grok, the artificial intelligence of X, confirmed the validity of it.
Matteo, these are more speculative ideas than the previously discussed about biological antimatter. Nevertheless, it makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
Anya, you know a lot. Let's summarize our discussion today.
From the predicted quantum classical frontier at the Planck mass, we might find primordial black holes. These cosmic entities could be the elusive dark matter we've been searching for. But wait, there's more. Enter the antimatter quantum classical frontier. Here, primordial antimatter sinks could be hiding the universe's missing antimatter.
Matteo, we should now summarize the complete series.
Yes, Anya. I think that it is time to summarize the complete series. But this is enough for today. Ciao, Anya. I love you, and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe, to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
One more thing, Matteo. We should talk about some everyday evidence that supports the validity of Einstein's special theory of relativity.
There's a common myth that we don't see evidence of Einstein's special theory of relativity in our daily lives. But the truth is, this theory is crucial for understanding the world around us. Non-relativistic quantum mechanics just can't explain our everyday experience. However, relativistic quantum mechanics explains it. So next time you hear that narrative, remember, Einstein's work is everywhere, shaping our reality.
Anya, I agree with you.
There are three crucial results that show why we need special relativity. First, it explains why there are only 100 chemical elements in the periodic table, not 1,000. Second, it helps us understand the classical nature of the macroscopic objects around us. Finally, it accounts for the existence of antimatter and why we don't encounter it in our daily lives.
Dear Matteo, you are well informed.
The following two graphs show two curves each, the blue ones from non-relativistic quantum mechanics and the red ones from relativistic quantum mechanics. Notice the red arrow indicating that quantum wave collapses are only predicted in relativistic quantum mechanics. They were reported in 2021 in the European Journal of Physics. A third graph illustrates the collapse of antiparticles' exotic quantum waves. This groundbreaking work was published by Professor Grave de Peralta in 2025 on his webpage in X, formerly known as Twitter. The collapse of quantum waves signifies a transition from quantum nature to classical, validating Einstein's special theory of relativity in our everyday experiences.
Anya, I agree with you.
There are three crucial results that show why we need special relativity. First, it explains why there are only 100 chemical elements in the periodic table, not 1,000. Second, it helps us understand the classical nature of the macroscopic objects around us. Finally, it accounts for the existence of antimatter and why we don't encounter it in our daily lives.
Dear Matteo, you are correct.
Thanks, Anya. This is all. Ciao, Anya. I love you, and we love our audience. Ciao, goodbye, adios, everybody.